Okay fellows, welcome to lecture 7 of module 2 of the video series Introduction to Data Structures in C. And today we will be talking about 6 common data structures which we are going to study in depth in the coming videos. Before we go ahead with these 6 data structures, let us get back and look into the actual a general overview of the type of data structures that are available and can be used in C language. Okay, so data structures can be basically classified, as we know, into primitive and non-primitive data structures. We know that there are 5 primitive data structures: character, int, float, and so on. Okay, void and so on. You know that. Okay, and in non-primitive we have linear data structures and non-linear data structures. Again, linear data structures can be static or dynamic. Okay, so we had talked about arrays and we had used arrays. So these were static data structures, as we had already talked about. Okay, and today we'll be in today's class and in the further lectures we'll be looking into some of the dynamic data structures as well. Okay, again, array is the conventional array which has been declared as static, so that becomes a static data structure. However, anyways, array can also be initialized in a dynamic way. Okay, we know that using some of the special instructions. Okay, they can be allocated in the heap and can be made dynamic. Keep that in mind. Okay, so when I say array, what I actually meant is the conventional array which has been declared in the static way. In nonlinear data structure we have trees and graphs. Okay, so from here on we'll be talking about arrays, linked list, stacks, queues, trees, and graphs. These are the 6 commonly used and prominent data structures, not only in C but in any other programming language that can be used and which need to be studied. Okay, so let's get started. First one is the array. Array, as we know, is a collection of similar data elements in consecutive memory locations in the stack. Okay, so the array has a name which points to the base address of this collection. Okay, so the array name is basically a pointer and points to the base address of the array. Okay, so the number of elements the array holds is called as the size of the array, and each element is associated with the index based on its position in the array. Okay, so the advantages of array is you can have a random access to the elements. Okay, and that makes things a lot easier and good for the programmer and fast as well. Okay, and you can use a single name to basically represent a lot many number of elements. The disadvantage of an array is you basically cannot, it is static, the conventional array is static and you cannot change the size of it. Okay, so that's a major flaw when we talk of arrays. The other one is you cannot basically stack different data types. Okay, an array basically stacks or accumulates a similar data type. That's another disadvantage of an array. Applications of array, even though array have a couple of drawbacks, they are basically the basic building blocks of lot more complicated data structures. Okay, and they are widely used for sorting algorithms, and they are on in a dynamic or in a static mode in what whenever required. Okay, so that was all about arrays. Okay, so the second data structure that we are going to talk about is linked list. Now, linked list is a sequential structure that consists of sequence of elements in linear order which are linked to each other. So as the name implies, it is basically n number of elements which are linked to each other. Okay, sequentially. So a linked list basically has 4 important parameters. The first one is the node. Okay, the other one is each node, as we know, has 2 parts. The first one is called as the data or the key part, and the second one is called as the link or the pointer part. The key part is the part where the actual data of that particular element gets stored. Okay, so the data can be a simple primitive data type like an integer, float, or a character, or it can be a complex data type like a array, a structure, or something like that. Okay, so basically it holds data. Okay, and the link part is a pointer which holds the address of the next node. Okay, so that is how the node gets interlinked to each other. So that is all about the node. Then the next one is the head. The address or the pointer which holds the address of the first node, okay, which is called as the head node, is called as the head. So head is nothing but a pointer, which, and as we know, a pointer is nothing but holds an address of another variable. Okay, so here every node is treated as a variable, and the head pointer basically holds the address of the head node, that is the first node. So that is what the head is. Okay, and the first node is called as the head node, whereas head is actually a pointer which holds the address of the head node. And then we have the tail node. The tail node is the node whose link gets terminated with the null. So as there are no more links in it is the last element of the linked list, and there are no more links there in the list, so we terminate the last link, okay, or the tail of the last node with a null. So this is called as the tail node. Okay, so some of the important operations that a linked list need to perform is the search. So any linked list, we should be able to search for a given data in the data path of the node for a given linked list. We should be able to insert new nodes in a given linked list, either in the beginning, in the end, or somewhere intermediately. So insert operation should be permissible, search operation should be permissible, and delete operation is permissible. So we will any given linked list, one should be able to delete the node at the beginning, end, or might be in the intermediate stage. Okay, so these are the three basic operations which are commonly used in a linked list. Okay, the next data structure which is very popular is known as the stack. Okay, stack is nothing but a stack of book. It follows the LIFO operation. Okay, so LIFO stands for last in first out. Okay, so a stack is again a collection of similar data type, very similar to that of an array, but unlike an array, you cannot have random access. The insert and the delete operation happens at the one end only. So the insert operation is called as the push operation, and we say we push the data into the stack, and the delete operation also, which happens at the same end, is called as the pop operation. So the data which goes in last has to be retrieved first. That is why it is called as last in first out. Okay, and the insert operation is called as the push operation of the stack, and the delete operation is called as the pop operation on the stack. Okay, and the elements which gets accumulated in the stack are called as the elements of the particular stack. So fairly simple. The push and the pop operations are the only two operations which are permissible in the stack. Apart from this, in order to add and remove data, apart from this, you can have some kind of operations so as to know the status of the stack, like p is empty and full. So p operation basically finds out whether an element is present in the stack or not. Okay, it's something like a search, but you cannot delete any elements or insert any element using p. Okay, and is empty is an operation which tells whether there are elements in the stack or not. Okay, and is full is an operation which tells me whether the stack is full. Okay, so if the stack is full, then is full basically gives you a true, or else it gives you a false. So these are the three operations which are used to find out the status of the stack, whereas push and pop operations are the operations which are used to insert and delete elements into the stack. Then we have another data structures which is called as a queue. Okay, as the name implies, the queue stands for a data structure which resembles the queue concept in real life. Okay, and in the queue concept we know that it is first in and first out. So insertion happens at the end and deletion happens in the front. Okay, and the one which comes first gets to go out first. Okay, so that is first in and first out. Okay, so keep this in mind. In stack, insertion and deletion happens at the same point, whereas in a queue, insertion happens at the back and deletion happens at the front, and that is why it is called as first in and first out. Okay, so the concept is very similar to that of a stack, but instead of the push operation we have what is called as the NQ operation, that is inserting the element at the end of the stack, and the delete operation which is called, or the pop operation in the stack is called as DQ operation in the queue, and this happens at the beginning, okay, at the front end of the queue. Okay, so that is the difference between a stack and a queue. Then another data type which is very popular, or data structure which is popular, is called as a tree. A tree is nothing but a hierarchical structure where data is organized in a very systematic hierarchical way. Okay, and they are linked together. Okay, say for example what is given out here is a tree. So a tree has a node very similar to that of a linked list, but this node can be connected to multiple nodes. Okay, so when this node is connected to only two nodes, it is called as a binary tree. Okay, so again, some of the concepts that one needs to know about a tree is each node is called as a vertex. A key. Each node can hold a key, and the node which is at the top of the tree is called as the root node. Okay, and the ones which follow from there on are called as the child node of the root node. Not only the root node, any node which precedes over the nodes which are below that is called as the parent node of the subsequent two nodes which are called as the child nodes. Okay, and a part of the tree of the entire tree is called as a subtree. Okay, so this is called as a parent, and these two are the siblings of this parent. That is what is the concept. Again, out here this is the parent and this is the sibling of that parent. Okay, hope you get the concept. This is a subtree of the entire tree, and again this can be a subtree of that particular tree. Okay, of this. So each tree can have multiple subtrees. Again, the nodes which are at the end, which further do not have any siblings, are called as the leaf nodes. Okay, which do not have any children, not siblings. The nodes which do not have further children are called as the leaf nodes. Okay, and the nodes which are at the same level are called as the siblings. Okay, and which share the same parent. Okay, and the total number of levels which are there in a tree is called as the height of the tree. So out here I have the root level, then I have this level, second, then I have the third level and the fourth level. So the height of this tree is 4. Okay, so these are some of the concepts that you should be aware of when we basically look into tree. Now applications of tree are very wide, and some of the most common ones are binary tree, where the data gets arranged in a particular way so that searching becomes very easy. Okay, and then we have binary search tree, and we have talked about heap. Basically the entire memory location of heap is organized in a hierarchical way, which is very similar to that of a tree. Okay, so we use this concept in basically doing memory managements of heap data structure, heap part of the memory as well. Okay, so these are some of the applications of tree data structures. Okay, and then we have what is called as graph data structure. So the next one is graph data structure, the last one. Okay, a graph data structure is nothing but collection of nodes which have data interconnected. Okay, so basically a graph has two things. One is called as the vertex and the other one is called as the edge. So a graph is nothing but a collection of vertices and edges together. Say for example out here, given out here, this particular graph has 4 vertices, 0, 1, 2 and 3. So this graph has 4 vertices. Okay, and it has 4 edges. Okay, so one edge is from 0 to 1, the other edge is from 0 to 2, and the other edge is from 0 to 3, and there is one more edge from 1 to 2. So this graph is nothing but a collection of vertices and edges. So that basically forms the graph data structure. Okay, and graphs can be of different types. There can be directional graphs and there can be undirectional graphs. Okay, and there can be graphs with self loops. So what are directed graphs? A graph in which the edge u comma v are connected, but that necessarily doesn't mean that v and u are connected, are called as directed graph. For example, here in this graph I have 4 vertices, 1, 2, 3 and 4, and there is an edge between 1 and 2, and there is an edge only between 1 and 2. Now this doesn't mean that there is an edge or there is a connection from 2 to 1. So these kind of graphs are called as directed graphs. Okay, so a typical way that you can make out that a graph is directed is that every edge is an arrow which points in the direction where there is a connection. Okay, and if there is a connection in either way, there will be 2 arrows pointing in the opposite direction. Okay, so that is called as a directed graph. A graph in which there is a direction as well as each node gets connected to itself, or say there are multiple nodes or a single node which gets connected to itself, is called as a directed graph with self loop. Okay, so here there is a connection between 1 and 2, and there is also a connection between 2 and 2. Okay, so this is a directed graph with self loop. Okay, and there can be graphs which are undirected. Okay, so here each vertex is connected to another vertex and there is no arrow or direction constraint on this particular link. So we say that 1 and 2 are connected, which means to say that 1 is connected to 2 and 2 is connected to 1. So these kind of graphs are called as undirected graphs. Further, some of the terminologies in graph are adjacency. We say 2 vertex are adjacent if there is an edge connection between them. So I say vertex 2 and 3 are adjacent if there is a connection, and if there is no connection between them, then I say they are not adjacent because there is no edge between them. So if vertex, even though they come sequentially as 2 and 3, if there is no connection between these 2 vertices, then we say that they are not adjacent. Okay, so that was about adjacency. Then there is a concept of path, a sequence of edges that we need to go through in order to reach from one vertex to another vertex is called as a path. Okay, say for example, in order to go from 0 to 2, I need to go from 0 to 1, and from that I need to go to 1 to 2. So this is the path that one need to take in order to go from vertex 0 to vertex 2. Okay, so that is what a path is. Then we have what is known as the order of a graph. So order of a graph is nothing but the number of vertices that it has. Okay, and typically a graph is being denoted by a matrix. So order of a graph is nothing but cardinality in simple mathematical terms. That is how many components or variables are there in that particular graphs. Okay, so order of a graph is nothing but its cardinality, or the amount of by which it can vary, or in other ways it is basically the total number of vertices that it has. Okay, and the size of a graph is basically how many edges are there in a graph, or how many edges could possibly be there in a graph. Okay, so say for example a graph with n vertices which is directed will have n into n minus 1 by 2 number of would be the size, is the maximum permissible size of that graph. whereas for an undirected graph it is n into n minus 1. That is the maximum permissible size for a undirected graph. So that was about size of the graph. Okay, then basically how do we represent graph? As I said, graphs are basically represented using a matrix or a linked list. Okay, say for example I have a graph like this. A graph can be represented in a matrix, and that particular matrix is called as the adjacency matrix. Okay, so what goes into the matrix is the nodes in the x and y as the x and y coordinates, and the linkages or the edges as the elements of this matrix. So from 0 to 0 I have no linkage, so there is a 0. From 0 to 3 I have a linkage, so from 0 to 3 I have a linkage. From 0 to 2 I have a linkage. From 0 to 1 I have a linkage. From 1 to 3 I do not have a linkage. Okay, so that is what is called as the adjacency matrix. Okay, so as we know, the concept of adjacency or adjacent is whether there is a edge existing. So that is where the name comes from. Okay, so it is a matrix of edges, okay, between two vertices, one given in the x as the x coordinate and one given in as the y coordinate of the matrix. Okay, so that was how we can represent graph using adjacency matrix. Similarly, we can represent graph using linked list, and such a representation is called as adjacency list. Okay, say for this given graph there is a link between 0 to 1. Okay, so 0 to 1 there is a link, and there is a link between 1 to 2. Okay, so 1 to 2, and there is a link between 0 to 3 as well. Okay, so 0 to 1, 1 to 2, and we have a link from 3 as well. So a given node or a given node is later on being represented as a linked list with respect to the nodes that it gets interconnected to. So node 0 basically gets connected to 1, 2 and 3. So we have a list of this kind of a linked list together. Okay, similarly node 1 can gets connected to 2 and 0. So need not be in the same faction, so but it's valid as well. Okay, so node 1 gets connected to 0 and 2. Okay, and say node 0 gets say node 2 gets connected to 0 and 1. So node 2 gets connected to 0 and 1, and node 3 is only connected to 0. So I can have a linked list in this fashion in order to represent a graph. Okay, and that particular linked list is basically called as a adjacency list. Okay, so some of the operations that are supported in a graph data structure is to check whether an element is present or not in the graph. Okay, so as I said, each node each vertex basically can hold some data in it. Okay, so whether a data is present in the vertex or not can be checked. Traversal. So a graph should allow us to traverse between multiple vertices or vertices of that particular graph. We should be able to add and remove vertices or elements into the graph. We should be able to find a path from one vertex to another vertex in a graph. So path or search algorithm should be feasible. Okay, so a graph basically should have these kind of functionalities in it in order to basically make it helpful. Okay, so those are some of the prominent operations that needs to be supported in a graph data structure. So in this 6 data structure there are some 6 basic operations that needs to be supported. First thing is traversing, okay, or traversal. Okay, so in any given data structure we should be able to traverse or go through all the elements of that data structure. We should be able to insert and delete element into this data structure. We should be able to search a particular element present in this data structure or in the given data structure. We should be able to sort or arrange elements in a very specific order for the data structure. Okay, and merging. We should be able to merge or club multiple data structures of similar type in order to make it more helpful. So those were some of the 6 basic operations that these data structures needs to support. Okay, so that's all for today, folks. Thank you for being with me, and hope you join me on my next video lecture as well. Thank you.